Swayam Prabha. Digital India. Educated India.
In this lecture, I am going to start discussions on the formulation of dynamics as given in the topic of analytical dynamics or analytical mechanics as formulated by Lagrange. We will start with the Hamilton's principle, which is a very important principle. This is a starting point which I will take to define dynamical paths and finally get to Lagrange's equation of motion. So, we will start from Hamilton's principle. What is Hamilton's principle? You know now that evolution of a dynamical system means evolution or motion of a point in the configuration space of that dynamical system. Evolution of a dynamical system means the motion of the point representing the configuration of a dynamical system in its configuration space. Suppose at time t equal to 0, the system configuration is completely known. As you know, any point in the configuration space represents the configuration, completely fixes the configuration of the system. Suppose at t equal to 0, t0, t equal to t0, we are at a point in the configuration space. Let that point be represented as q0. So, q0 represents the configuration of the dynamical system at time t equal to t0. Everything is now happening in the configuration space. We are looking at the system in the configuration space, the evolution in the configuration space. Now, at t equal to t0, it was at configuration q0, which is known to me. I have seen it. Then I do not look at that evolution. I close my eyes and I open my eyes at time t equal to t1. Of course, it is a dynamical system, it is evolving. Therefore, I expect that in the configuration space the point is moving and it will move at time t equal to t1. Let us say it is at q1. I open my eyes and find that the dynamical system is sitting at point q1, it is a new configuration of the system. At time t equal to t0, I knew the configuration of the system. At time t equal to t1, I know the configuration of the system, but I have no information what happened to the system in between, how it moved. I suppose I do not have that information. I have seen the system in configuration 1 at configuration 0 q0 and now I am seeing it at configuration 1. The question arises, can we determine the path taken by the system between q0 and q1? How did it evolve from q0 to q1? This is the question that arises. Can we answer this question? The answer is yes, we can answer this question using the Hamilton's principle. Hamilton's principle is a very important principle that tells us about this path and which is at the foundation of analytical mechanics. Here I have shown the configuration space. This can be a very high dimensional space, as you have seen through examples. I have drawn it in a plane for simplicity. I know the coordinate locations q0 and q1. In between I can make guesses, I can have various paths. Therefore, at time t equal to t0, remember these paths are parametrized by time. As time evolves, the paths are developed. So, suppose as time evolves, the point can move on the green path or on the blue path or on the brown path. Now, these are, but which path I do not know, there can be infinitely many paths, I do not know. how does Hamilton's principle help us? It says a system will take that path which extremizes the action. We have introduced new terms, action. Extremizes means either it minimizes or maximizes. A single term for minimization or maximization is extremization. Therefore, the system, what Hamilton's principle tell us is the system will take that path which extremizes the action, or sometimes also known as the action integral. What is action then? Action is this integral. This integral is a function of the path. This is a definite integral with time over time, with these time limits over which I have seen the system. Suppose it evolved from T1 to T2, therefore, it is an integral over time of a certain function. This function, the integrand is known as the Lagrangian, to honor Joseph Louis Lagrange, who developed this form of mechanics. Okay, Lagrangian, fine. What is Lagrangian? Then we need to know. Now, that is dependent on the system we are looking at. Let us get back to Hamilton's principle once again. Therefore, a system, Hamilton's principle tell us the system will take that path which extremizes the action integral or action, and action is defined as a time integral of the Lagrangian. Lagrangian, as you can see, is a function of the path in the configuration space q as a function of time. See, q is a function of time. If I know this, I can also find out q dot. Of course, this can be multiple elements. I will write like a vector to show that there are multiple elements in there. So, if I know q as a function of time, I will also know q dot, I can calculate. And if I know the structure of Lagrangian, we will see that very soon. I can substitute in this Lagrangian, find out the Lagrangian as a function of time, explicitly as a function of time, and integrate over time. That should not be a problem, from T1 to T2, and calculate the action. I can take various paths, I can make many choices of paths and keep substituting in the Lagrangian, calculating rate of these generalized coordinates q, and keep on substituting in the Lagrangian, integrating them and calculating the value of a. And value of a, note, is a function of the path followed by the generalized coordinates q, because in the configuration space the generalized coordinates are the coordinates. Therefore, I can keep doing this and I will choose whichever is either minimum or maximum, that we will see. This action is known as a functional. It is function of a function. What is that function? That is the path of the generalized coordinates, the variation of path with time, q as a function of t, the evolution of the generalized coordinates as a function of time. This is the function whose function is the action. So, action is a function of another function, that another function is the time function of the generalized coordinates. Therefore, to calculate action I need another function completely specified over this time interval T1 to T2. For light, it is very simple. The action is integral over time from T1 to T2, integral over time, integral dt from T1 to T2. Why? Because light minimizes time. So, action is minimized. This is Fermat's principle. It is very simple for light. Now, this Lagrangian will be obviously be different for different systems. So, for light that Lagrangian is 1, for light Lagrangian is 1, light minimizes the time it takes to travel between 2 points. For example, light ray starts from A, how will it reach B? It will minimize time. You light on a bulb at A, how will that light travel to B? It will travel by the minimum time path. And if this space in which light is moving is homogeneous, isotropic, etc., all those nice properties are there, it has got a unique speed, then it will take the shortest distance path, because shortest distance will minimize the time, then you will have the shortest time. Therefore, straight line path is the shortest time path in a homogeneous isotropic space. In a homogeneous isotropic medium, the minimum time path is same as the minimum distance path. So, it is a straight line. Introduce a new medium on that path between A and B. That means, B lies in a different medium now, where the speed is different, speed of light is different. Then this shortest time path is not the straight line path. The shortest time path is that red path. Straight line path is no longer the shortest time path, and that is why we have the phenomenon of refraction shown here. And you can find out that path by minimizing this integral. Now, for mechanical system, it so happens that Lagrangian is equal to the kinetic energy minus the potential energy. This is very important, kinetic energy minus the potential energy, and this is what is found. Lagrangian for a mechanical system is kinetic energy minus potential energy. The Lagrangian that sits in the action integral is kinetic energy minus potential energy, and that leads to the correct equations of motion. And in the case of mechanical systems, it so happens that the action is minimized. We will come back to that. Now, we discuss a little bit about how do we extremize a functional. We were discussing Hamilton's principle says we have to extremize the functional, we have to find out such a path which extremizes the action integral. We have to find a path in the configuration space as a function of time, how these coordinates are varying as functions of time. We have to find such these paths and calculate the action and extremize and see minimize, let us say minimize, find out that path which minimizes the action. How do we do it? Suppose I take path P1, this path P1 which is the brown path. Suppose I represent that path in terms of time, such that at time t equal to t0 it is at q0, at time t equal to t1 it is at q1. I can do interpolations and find out such functions of time which in which I put t0 I will get q0, q0 is known to me, remember. Similarly, I will put t1 I will get q1, rest what happens in between is according to the choice of my path, but at least these two end points must be respected. I can calculate the action value of that action integral a1. I can take another path p2, the blue path, I can calculate the value of action a2. I can take p3, I can calculate value of action a3, and I can keep doing this on and on forever, infinitely many paths. I have to do it forever. I will never possibly be satisfied. So, therefore, this approach of extremizing is either maximizing or minimizing. If it is minimizing, then I have to find out some ith path such that ai is small, less than or equal to of all other paths that I have taken. It should be less than or equal to all other paths. If it is maximizing, then a I should be greater than the value of a I must be greater than those calculated for all other paths. But is this approach practical? This is not practical, because you have to keep taking paths and you will never possibly be satisfied. Let us go back a little bit and look at how we extremize a function, not a functional. Action integral is a functional, action is a functional, it is function of a function. Let us see how we extremize a function. Let us say a function function f, which may be a multivariable function, it is dependent on a number of variables x1, x2, etc. How do we find out the maxima or minima of functions? We consider a point, let us say x star. Suppose we say that okay, x star is an extremum point. What should be the characteristic of this point, or what qualifies this point as an extremum point? That if I move out from this extremum point a little bit, infinitesimal moving out from this point, the function value is not going to change. That is what we use. The function value should not change at extremum. Of course, whether it is minimum, maximum or an inflection point, that we will decide later. But how to find out these extremum points? We take a point which we think that it is an extremum point, add a very small quantity to it. Now, here it is a vector quantity. Therefore, what it means is an arbitrary direction in the x space we are moving, very small amount, minus the value of the function at our extremum point, divided by epsilon, this vector. Now, this division by vector with vector going to 0, this must be equal to 0. Now, what this gives us is the gradient operator. This means that the gradient of f at x equals to x star must be equal to 0. This is definition of gradient, and epsilon vector is a perturbation vector which should be arbitrary small. So, this is the gradient. Now, we come back to our problem. We think of this space of functions. Now, this is going to be a little stretch of imagination. On this axis, we have different functions of the generalized coordinates as functions of time. So, these are functions of time. Every point in the horizontal axis represents a variation or motion of the generalized coordinates, or the evolution of the generalized coordinates as functions of time, each point. This is a little hard to imagine first, but I mean by a little stretch of imagination you should be able to visualize this, that every point on the horizontal axis is actually a time function and a vector time function. Then we can think of the action as a value corresponding to it. Actually, this should be action. This should be action. So, corresponding to a point, a choice of the evolution of the generalized coordinates over the whole time range, I can calculate the value of the action. So, this is just a visualization. I mean, this has no consequence as such. And on the right, I have shown the configuration space. The figure on the right is the configuration space in which the dynamical system is evolving, and on the left I have the action versus the choice of path, and each point represents a path as a function of time over the whole travel. Limit as epsilon tends to 0 of the value of action calculated at a perturbed path. Now, if q star is a path, it is this point, q star is this point, it represents a complete path. Remember, this represents a complete path. So, one q star, so this is q star, it represents the complete path, the brown path. That point represents a complete brown path, and I take a small perturbation of this path. Now, when I take this perturbation, I should be careful that I should not perturb the end points. End points are not to be perturbed, because those things I definitely know, though the system was at those points at the start and at the end. In between there can be arbitrary variations. Therefore, a neighboring point of q star, let us say this point, is another path, this purple path represented by q star plus some small value times eta. Eta is of course another vector. This is a perturbed path and a point on this figure in the left. This is a completely a visualization tool. So, we are perturbing, as if we are perturbing paths here on the in the configuration space on the figure, and in the figure on the left we are perturbing points, because points on the horizontal axis represents path. Okay. And I take the difference of the action calculated at the perturbed path minus the value of the action on the original path divided by epsilon, and that must be equal to 0, this must vanish. This is direct analogy of minimization or extremization of a function. We are now extremizing functionals. So, x axis, the horizontal axis are functions, and the action is a function of these functions. We write this just like we wrote, we came to the definition of the gradient operator. Here we define a delta operator, which is known as the variation operator acting on the action. Like in the case of functions, it was the gradient operator acting on the function must vanish. Here the variation operator delta acting on the action at q equal to q star, this path must be equal to 0 if q star is to be an extremum path. Delta is known as the variational operator. It is a variation of the action which vanishes. Eta t is a perturbation or variation function which is absolutely arbitrary. I can get back to q star from the perturbed path. You see, from the perturbed path, this is the perturbed path, I can get back to the original path q star by just putting epsilon 0. Eta is any arbitrary path such that eta at t 0 and eta at t 1 must be 0. This is the only condition required on eta. Eta at t 0 and eta at t 1 must be 0, so that I do not vary my initial and final configurations, because that I know, I have recorded it, I have seen it. Therefore, I am not allowed to vary those points. Therefore, eta, which is the perturbation function, that must vanish at these two extremum points, end point configurations being known. Let us visualize this in another way. Our generalized coordinate space, the configuration space, which is the space of the generalized coordinates, is sitting here, and as the system is evolving over time, I extend the time axis, and there are copies of this configuration space that is moving with time. At time t equal to t 0, I know this configuration fixed. At time t equal to t 1, I know this configuration fixed. The brown path is my the optimum path, which is actually the dynamical path, which I actually want to find out, and the perturbed path is the blue one. At any time instant t, you see this there is a gap between the optimum path or the dynamical path, the true dynamical path, and the varied path, and that variation on the path, again now this variation operator is acting on the path, on the coordinate, generalized coordinate. So, delta q is the variation of the generalized coordinates. The variation of the generalized coordinates is represented as delta q, and which is nothing but epsilon eta, variation of generalized coordinates. This is the variation of the generalized coordinates is equal to the perturbation that I have added. The variational operator on the generalized coordinates I have written. This is known as virtual displacement vector. Why the name virtual? Because it is not real. Real displacements take place as time evolves. Virtual displacements take place with time frozen, as shown here. At this value of time being frozen, this is the virtual displacement. This is the vector of the virtual displacement, which is represented by epsilon eta. This is known as virtual displacement vector. With time frozen, whatever is the difference between the actual dynamical path and the perturbed path, that is known as the virtual displacement. Now, Hamilton's principle, once again we come back to Hamilton's principle. It says a system will take that path for which the variation of the action vanishes, or delta A, delta operator operating on A is 0. We have looked at delta operator operating on the action, and we have also looked at delta operator operating on the generalized coordinates. When it operates on generalized coordinates, they are called the virtual displacements. For a mechanical system, the action is minimized, and what sits in the action for a mechanical system? Its integral over time from t1 to t2 or t0 to t1. The Lagrangian is kinetic energy minus the potential energy. So, this action, this integral is minimized in the case of a mechanical system. Let us now apply whatever we have learned to derive the equation of motion, what is commonly known as the Lagrange's equation of motion. We have the action, and that is in terms of the Lagrangian. Variation of action must vanish, that implies this delta. Now, this delta commutes with the integral, because delta is the variation operator which acts on perturbing paths. It has nothing to do with time, because remember the variation is always with time frozen. Therefore, this delta operates on the Lagrangian directly, it goes into the integral and operates on the Lagrangian. Now, this delta operator has a property. So, let us look at some properties of the delta operator. It is very similar to the total derivative operator, except that because time is frozen, it will not derivate time. This is a very important difference between delta and d. D operator, the total derivative operator, derivates time as well, whereas delta will not derivate time, and it commutes with the time derivative d dt. Delta of d dt is d dt of delta operator. So, it commutes with the time derivative. Always keep this picture in mind that delta gives us the variation on the path with time frozen. Therefore, delta will not derivate time. With this understanding of delta, we can start using delta as a total derivative, except that it will not derivate time as shown here. So, delta of the Lagrangian is del del q of the Lagrangian dot delta q plus del L del q dot delta q dot. There is no term like del L del t delta t, because delta t is not existing, there is no variation in the time direction. But had it been total derivative, then there would have been such a term, but the variation operator works on the system with time frozen. Therefore, we have this, otherwise it is like the total derivative operator. And what is del L del q vector? That is this vector del L del q1, del L del q2 up to del L del qn. So, we have to derivate the Lagrangian. Lagrangian, remember, is a scalar function, action is a scalar quantity. Lagrangian, which is kinetic minus potential for a mechanical system, is a scalar quantity. For light, it is one scalar quantity. Therefore, this Lagrangian scalar has to be derivated with respect to these all these generalized coordinates, and that is del L del q vector. Similarly, del L del q vector dot, I mean this time derivative of the generalized coordinate, the second term. This you should write out and then understand. Now, if I integrate by parts, because this is a time integral and here sits delta of d dt of q, and we know that d dt commutes with delta. I can integrate this second term with respect to time. If I do that, so I integrate by parts. First function, time integral of the second function. So, this is the first function. When I integrate over time the second function, I get delta q, and this is to be evaluated at these two boundaries, time boundaries t0 and t1, plus we have inside the integral minus. So, this is the continuation of integration by parts, first function integral of the second function minus integral of derivative, time derivative of the first function, integral of the second function. There is a dot product sitting in between, and this term goes as it is. Now, why have we done this? Because inside the integral I have now delta q. Initially I had delta q dot, but now after this integration by parts I have delta q here. Therefore, I can pull it out and use the condition that delta q is arbitrary, the variation is arbitrary. At any time frozen, we have seen what is delta q, this delta q can be arbitrary. Okay. What about this boundary term, the term which has to be evaluated at time boundaries t0 and t1? At t0 and t1, the variation of q, what is it? It is 0, because eta, remember delta q is nothing but epsilon eta, and eta at time t0 and time t1, they are 0, both at both these ends eta is 0, therefore, delta q must be 0, because there cannot be any variation at the time boundaries. This must be 0 at these two time boundaries. Therefore, this term, the first term, the boundary term drops off, what we are left with. So, boundary term drops off because eta at t 0 and t 1 they are 0. What we are left with is only this term in the integral, and this must be 0 because the action must vanish, the variation of action must vanish. Therefore, this must be equal to 0 for arbitrary choice of delta q. If it is to be 0 for arbitrary choice of delta q, then it means that this itself must be 0, because delta q is an arbitrary variation. This is known as the Euler-Lagrange equation in a general context. In the special context of dynamical system, this is known as Lagrange's equation of motion. The number of equations, how many equations will we have? We will have as many equations as there are generalized coordinates. So, we will have n generalized coordinates because the system has n degree of freedom, let us say, then we will have n equations of motion. Just as a quick example, we will look at the pendulum example, equation of motion of a simple pendulum. Generalized coordinates we know is theta. Lagrange's equation, straightforward, d dt of del L del q dot minus del L del q. This is the form of Lagrange's equation for a single coordinate theta. Now, for a mechanical system, we have noted that the Lagrangian is kinetic minus potential energy of the system. Kinetic energy is half mass velocity square. Now, here we need the physical coordinates, but we can always write in terms of the generalized coordinate rates. Velocity is L theta dot, the magnitude of the velocity is L theta dot, therefore, velocity square is L square theta dot square, and the potential energy is minus mgl cosine theta, where datum is taken as the x axis. Note that I have represented the kinetic and potential energy expressions all in terms of the generalized coordinates, and then I will define the Lagrangian in terms of the generalized coordinates. It is t minus v, please note that t minus v, and v comes with a negative sign, therefore, it has become 1/2 ml square theta dot square plus mgl cosine theta. This is t minus v, that is Lagrangian. Now, I start calculating the terms of the Lagrange's equation of motion. First, I calculate this del L del q dot or del L del theta dot, in this case partial derivative of the Lagrangian with respect to theta dot. Now, in mathematics you must have learned this. Partial derivative with respect to theta dot is nothing but derivative of the first term, because theta dot appears only in the first term, and that is m L square theta dot, and d dt of this, mass is constant, L is constant, therefore, we get m L square theta double dot, and del L del theta, it is minus m g L sin theta. Del L del theta, partial derivative of the Lagrangian with respect to theta, theta appears only in the second term of the Lagrangian, and therefore, partial derivative with respect to theta is minus m g L sin theta. Now, we will plug in all these things in the Lagrange's equation of motion, this minus this. So, please be very careful about the signs, and my suggestion is to write down each and every term like this and then plug it into the equation of motion. Otherwise, there is a great chance of making mistakes with the sign, and once I plug in, it becomes m L square theta double dot plus m g L sin theta, which I can simplify to get back the familiar equation of motion of a simple pendulum. So, I have demonstrated the application of Lagrange's equation for the simple pendulum. To summarize, we have discussed the Hamilton's principle for determining dynamical paths and looked at Lagrange's equation of motion. With that, I will close this lecture.